chemical, usually we call this a violation, because if it is Q0, Q bar becomes 1 as per the rule, but it is violating the rule. Correct. When I am getting the violation rule in my NOR latch is when I am putting what? S is equal to 1 and R is equal to 1, correct? And R is equal to 1, S is equal to 1, I am getting what? Q is equal to 0, Q bar is also 0. Now let us understand what is mean by metastability. You are asking question that what is mean by the metastability. Okay. Now you understand this statement. After this condition, what I am going to do, I will be putting S is equal to 0, R is equal to 0. R is equal to 0. Now you can tell me what is the Q1, Q bar? After this condition, if I put S is 0, R is 0. What is Q1 and Q1?
1, 1.
How you say 1, 1? Means, let us understand. This is
undetermined. 0, both are 0, 0.
See, okay, you understand my statement here. Now I am getting S1 and R1, Q0, Q bar is also 0. After this condition, I am putting S0, R0. Okay?
Yes, sir.
If I start analyzing from the first gate, my analysis will start from the first gate, then I will consider this input as 0, right? This input as 0. If it is 0, 0, then Q becomes what? 1.
1.
If I start analyzing from here, I am assuming that this input is 0. Because this Q bar is 0 here. Once this is becomes Q becomes 1, this becomes what? 1, 0. 1, 0 means what happens here? This becomes 0.
Yes, sir.
Correct? Now Q is equal to 1 and Q bar is equal to 0. When this has happened, if my analysis
Operation starts from first gate.
From the first gate, correct? Analysis from the first gate. First gate. Correct. Suppose I will be putting after this condition, if I am putting again S is equal to 0, R is equal to 0, if I start analyzing from the second gate, let us take second gate. If I am putting S is equal to 0, R is equal to 0, now my analysis start from the second gate means this becomes 0, right?
Yes, sir.
This is 0. 0, 0 means now Q bar becomes 1.
Yes, sir.
When Q bar becomes 1, Q is equal to 1, 0.
Yes, sir.
Now in this case, I am getting Q is equal to 0, Q bar is equal to 1. Correct?
Yes.
This is happened after this condition. S is equal to 1, R is equal to 1. Is it you are exactly sure that what is the value of the Q for this states?
No.
After this, if I put S0, R0, you are guaranteed that my Q is 0 only. My Q is 1 only. Can you guarantee that? No, right?
Yes, sir.
If the propagation delay of this gate will be lesser than this gate, if this gate will get to the fast input of this 0, this always gives 1 and this gives 0. If this gate will get the fast input of this 0 after this condition, then this gives me 1 and this gives me 0. You are not going to show that what is the value of Q. That state we call it as an unreliable state. Unreliable state, or we call it as a metastability state. Metastability is nothing but you are not exactly telling that whether my Q value is 1 or it may be 0. This state representation is nothing but metastability state. You are not guaranteed that Q is equal to 0 or Q is equal to 1. So when you get this metastability state or unreliable state in the latch, in the NOR version of the latch,
Equal to 1 and R equal to 1.
after this condition, you should tell, after this condition, if I am trying to put a memory state, S0, R0 means we understand that. S0, R0 means our memory state, right? Here, in this case, you are exactly telling that S1 and R1, Q is equal to 0, Q is equal to 1 and Q bar is exactly you are telling. This should be my Q and Q bar. After that, if you put S0 R0, you are saying that it follows the previous state. In this state also, S0 R1, you are telling that Q is equal to 0, Q bar is equal to 1. After this, if I put S0 R0, it is following the previous state. There is a guarantee you can tell that what is a Q1 Q bar. But this SE00 means memory state. 0 means reset state, 10 means set state. But after violation state, if you put S0, R0, then it is going to the metastability. This is what metastability. You are not guaranteed that what is the Q1 Q bar value. Okay, this is a metastability. But when you are talking about flip-flops, you are talking about the timing considerations.
Yes, sir. Setup.
Timing considerations. What timing considerations is? First one is nothing but clock pulse width. First one. Second one is setup time. Third one is hold time. So your flip-flop should follow this timing consideration to get the desirable output of the flip-flop. So clock pulse width means, let us take JK flip-flop. This is a JK flip-flop. This is the clock. This is JK input. Q1, Q bar are the output. Okay. This flip-flop will work only when my clock on or off pulse width should be 1 nanosecond. So this, let us assume that the clock pulse width will be 1 nanosecond. T on and T off should be 1 nanosecond. So this is a clock pulse width. Minimum clock pulse width I should provide to my flip-flop to get the Q1 Q bar, create desirable Q1 Q bar output. In case if I am reducing this clock pulse width to say for example 0.5 nanoseconds, your flip-flop won't give the desirable output. It will lead to what? Metastability problem. Metastability problem means unpredictable behavior of the Q1 Q bar. For the set of inputs, what is a pair of inputs you are applying? For Q1 Q bar should be unpredictable. That state we call the metastability state. So when you are working with the flip-flop, you should ensure that what is the minimum clock pulse you should maintain. If you fail to do that, your flip-flop leads to the metastability. You can ask me one question that where I will come to know all these details. Where is clock pulse? Suppose I am using flip-flops. Where I will get this data? So this data basically it should be available in the data sheet. Okay, what is a clock pulse? What is setup time? What is the hold time you should follow to avoid the metastability problems? So this is the one first timing consideration is a clock pulse width. Second one is nothing but setup time. What is setup time means? If I talk about the clock, this is my clock. Suppose it is a positive triggering flip-flop operation. This is here. What is a positive edge means? Whenever the transition takes from 0 to 1, output changes, it will stay remain same until the next positive edge comes. Correct? This is operation for positive edge triggering flip-flop. The minimum time before latching will take place of this whenever the rising edge comes. So this minimum time before the latch up, that time we call it as setup time. So flip-flop to do a latching operation, minimum time it is required. That minimum time we call it as setup time. Means name implies here. Setup means getting ready. So this time we call it setup time. For the rising edge. Falling edge means this time. Before this falling edge comes, this time we call it as a setup time. What happens during the setup time, whatever the input you are applying to the flip-flops must be maintained stable during this setup time. If you are changing during this setup time, suppose D flip-flop you are using, if you are changing D flip-flop during this setup time, again your flip-flop leads to the metastability problem. So that data should be, the input data, whatever you are applying to the flip-flop, the data should be remains stable during the setup time and hold time. What is the hold time means? After latching takes place. This time is nothing but hold time for the positive edge triggering flip-flop. Negative edge triggering flip-flop means this is the time after latch up takes place. This time is nothing but hold time. So during the setup time and hold time, you should maintain the stable inputs. You should not change the input during the setup time and hold time. What happens if I'm going to change this? Then flip-flop leads to unpredictable. You are not guaranteed tell that what is a Q and Q, but that state we define as a metastability problem. Did you understand? Yeah, am I audible? Hello?
Yes, sir.
Did you understand what is meant by metastability?
Yes, sir. That is set up and hold time is means
What?
I didn't get it clearly, sir.
Okay. Let us do one thing. Yeah. Did you able to see this?
Yes, sir.
So this is my flip-flop, D flip-flop.
Yes, sir.
Okay.
Yes,
This is
sir.
the input.
Yes, sir.
This is the clock. I'm applying to this. So this is the input I'm applying to my flip-flop. This is the clock. This is the clock. But usually we'll clock, rating a clock like what? How you are rating the clock with ideal clock?
Square like
Also, there is a square like shape.
yes, sir.
But practically it is not true, right? It will take some delay to take the transition from 0 to 1. The transition I am here. Okay.
Yes, sir.
And similarly, this is my clock on pulse rate. Again, it is taking the transition from 1 to 0.
One, two, three.
This is raising it and this is falling into the clock. Okay. You can see this time period. So before raising edge happens, this time period we call it as what? Set of time. For positive edge triggering flip-flop I'm talking about. And after this raising edge happens, this time period we call it as a hold time.
Yes, sir.
Okay. So during this time, what I have to do, I should maintain the stable, data must be remain stable during this time. Means you are maintaining input is 0, it should be 0, or it may be 1, it should be 1. What happens? I'm changing input 1 or 0 here. I'm changing the input during this setup time. Okay.
Yes, sir.
Then
It's
this
changing
flip-flop
before the
this flip-flop leads to
It's changing.
metastability.
okay, sir.
If I'm changing the input during setup and hold time, then my flip-flop Q should be the unpredictable behavior.
Yes, sir.
So
Sir.
we should. Okay. Yeah. Hello.
Sir. Whole time, I think whole time is extended up to where the transition starts from 1 to 0 exactly.
No, hold time is this is the one. If I'm writing, okay, let me write.
Up to before transition, it is stable, no, sir. So we need to extend before the transition whole time.
So, okay. If I'm writing the ideal clock like this is ideal clock, correct?
Yes, sir.
So, these are raising edge. If I'm talking about this time period is nothing but setup time.
Yes, sir.
It is a minimum amount of time period before clock transition happens. Means 0 to 1 transition happens. This is setup time. Once transition happens 0 to 1, it is a minimum time period after the transition. Means 0-1 transition means positive edge. This is nothing but a hold time. This with respect to the rising edge, positive edge triggering. In the case of negative edge means this is a negative edge. Transition happens from 1 to 0. This period we call it as a setup time before 1 to 0 transition happens. And this period we call it as a hold period for negative edge, 1 to 0 transition. Here also, before transition, this time period is nothing but setup time. And then after transition happens, this minimum time period we call it as a hold time. This is a hold time. That is what I was representing. You can see. So we should maintain the stable input.
Time only transition to 0 to 1 or always a clock raising from 0 to 1? It depends on both falling and rising and falling.
No, you can see in this case I'm using one flip-flop. Positive edge, right? This is a positive edge. This is a positive edge. So that I'm referring this setup time and hold time to 1. You know the transition.
Yeah, for positive edge, it always depends on rising edge. Rising edge.
Correct.
Correct.
Should be rising edge. Suppose you are talking about a negative edge. Negative edge triggering flip-flop. Then the setup and hold time should be applicable to what? Whenever the transition takes from 1 to 0, falling edge.
Yes.
During this time, you should maintain the stable input. So there are some techniques are there. Suppose there is a setup violation is happened. Suppose you are using some flip-flops. Setup violation happens. If you are reporting that setup violation is happened. Means setup violation is happened means what happening in my flip-flop? Someone tells that there is a setup violation is happened in this circuit, in this flip-flop. Means how setup violation is happened in this flip-flop?
Is starting before the actual time period transition.
Yes. The input as changing during the setup time. That's why I'm reporting this. That's why I'm getting the setup time violations. Setup time violation is happened means there is data is not maintained, remains same during the setup time. Data is changing during the setup time. That's why I'm getting the setup time violation. To avoid that, what I need to do? Can you tell me any technique which you can get an idea to avoid this setup time violation?
Yes. Or instead of level training, we used to edge triggering.
No, I'm talking this with respect to
Okay.
means change happening in the setup time means what you can do. You can forward this signal to after the setup time, or you can delay this. If you delay this here and maintain the stable input during the setup time, so that you can avoid the setup time violations. Then setup time is setup time happening means that input is not stable during the setup time. Input is changing. That's why I'm getting the setup time violations. To avoid that, you can delay the clock or you can delay the input. Whatever the input you are giving, you delay that. If I'm delaying that, I can maintain the stable input during the setup time and hold time. How you can delay here is nothing but by putting a buffer. Buffer is used to introduce the delay in the circuit, right? One approach I'm talking about to avoid the setup time and hold time violations. You introduce the buffer between the flip-flops, so the data will be getting delayed. This is one common way approach to avoiding the setup time and hold time violations. Okay.
Yes, sir.
So what you should think when you are using the flip-flop, what you need to do that, considering what things we need to consider to work with the flip-flop.
Timing considerations.
Timing considerations. You should know that timing consideration, like how much pulse width I should maintain, what is setup time, and what is the hold time of the flip-flops to get the desirable output. If you are failed to maintain this timing consideration, then it leads to metastability. In simple terms, metastability term is nothing but you are not going to exactly predicting the output. What could be the Q and Q bar output. That state we call the metastability state.
Sir,
Yeah, then you're talking about racing, right? Racing is
Yes, sir.
different from metastability. Racing
Yes, sir.
is different. Racing is different from your metastability. Metastability means unpredictable behavior. Okay. Racing means metastability. Racing means let us check output will be constantly changing like this. 0 to 1, 1 to 0, 0 to 1, 1 to 0. Like this is 1. Or if it is high, suddenly it goes low. This behavior we call it as a racing behavior. Some bounces happens. This we call it bounces, or commonly we call this glitches. Glitches. So glitch is nothing but a narrow unwanted pulse or a transient, so which appearing at the output of the circuit. So that we call it as a glitches. So combination of 0 glitch. This is glitch 1 we can call. This is glitch 1. This is nothing but a glitch 0. Glitch 0. Combination of this is what happening in racing happening here. 0, 1, 0, 1. Instead of this output is 1 or 0, there is a races happening here. So this behavior in the circuit we call it as a racing behavior. Did you understand? Any questions here? Metastability is totally different from racing.
Sir,
So racing
metastability.
Yes. Hello.
Metastability occurs in SR and this race around occurs in JK flip flop, so you can control like that.
Yeah, you can say like that. So when racing is happening means let us take the flip flop. I'm going to write the NAND version of the flip flop. NAND version of the flip flop. This is Q and Q bar. This is let us take JK flip flop.
Yes, sir.
This is the clock. This is the clock.
Yes, sir.
And there is SR flip flop. Also, it is SR flip flop. For S is equal to 1 and R is equal to 1, you will be getting violation state. To remove that violation state, you are introducing the feedback like this.
Yes,
That
sir.
the violation state is converting into the useful state, you are introducing the feedback like this. Correct. So in this case, what happens? This is my clock. Let us run the clock. This is a clock. This is okay when j is equal to 0, k is equal to 0, memory state. J is equal to 0, k is equal to 1, reset state. J is equal to 1 and k is equal to 0, set state. But when j is equal to 1, k is equal to 1, when you give the clock to this, what happens? Q is nothing but Q is happening a racing. Means uncontrollably it is changing 1 to 0, 1 to 0, 1 to 0 like this. Again, when Q is equal to 1, in this case, J is equal to K is equal to 1, there is a racing is happening. So this state we call it a racing behavior. This is a racing behavior. Okay. This is a racing behavior. If you are not maintaining the minimum clock pulse width, clock pulse width, and then set up time, hold time, then Q is unpredictable behavior. Q goes to the metastability. So this is the difference between metastability and the racing. Racing is nothing but constantly changing. Q is changing very constantly 0, 1, 0, 1, 0, 1, 0, 1. That mechanism we call it as racing or racing behavior. Did you understand? So when you correlate metastability with the racing. This is how racing means glitches. Glitch 1, glitch 0 combinedly you can call it as a racing. Okay, unwanted signals which appear in the output of the circuit. Metastability means Q cannot be exactly predictable. Okay, so that state we call it metastability.
Sir, NOR latch gives meta stability state and NAND latch gives toggle store erase around.
No. Both your NOR latch and NAND latch both are it will use the unreliable state. Means, see in the NOR latch, this is a NOR latch, right? When S is equal to 1 and R is equal to 1, if you put S is equal to 0, R is equal to 0, you will be getting unreliable. You are not, whether you show that Q is equal to 0 or Q is equal to 1. No, right, after this state, if you put 0 or 0. This is nothing but metastability or unreliable state or unpredictable behavior. Unpredictable behavior is nothing but a metastability. This is the case of NOR latch.
Yes, sir.
Now coming to the NAND latch. This is a NAND latch, right? We can write NAND latch. This is the one. This is a NAND gate. This is a NAND gate. So this is complement, right? Complement of your NOR latch. This Q and Q bar. Here S bar, R bar. If I read the characteristic table to this, if it is 0, 0 means violation state. 0, 1 means 1, 0 state. 1, 0 means 0, 1 state. 1, 1 means it is a memory state.
Yes, sir. Okay, sir. Got it.
Now you can tell me when you will get unreliable state in the NOR latch. When you will get
NOR latch.
This is a NAND latch. This is a NAND latch. NAND latch. When you will get the unreliable state?
S bar 0, 0, R bar and 0, 0.
Yes, S bar is 0, 0. S bar is 0, 0. After that, if you put the memory state, this is a memory state here. If you put after this condition, if you put S1 and R1, then it is a metastability. It means unpredictable.
Okay, sir. Okay, sir.
Right, you understand?
Yes, sir. Understand. Sir, while we are analyzing flip-flop by using initial condition 0, 1, sir, S and R. Is it possible to analyze using 0 and 0?
No. Okay.
So we have to take one condition as no, sir.
Not one condition. Why you need to take any one condition? Let me clarify this. Let me draw the NOR latch.
Yes, sir.
Correct? This is R and this is S. I don't know what is the value of Q1, Q bar. Let us assuming that it may be X means what? 0 or it may be 1.
Or 1.
Here also it may be 1 or 0. Correct? I don't know what is a Q1, Q bar. Okay.
Yes, sir.
Now we'll understand. Now I'm putting S is equal to 1 and R is equal to 0. I'm not considering what is Q1, Q bar. Correct? I'm putting S is equal to 1 and R is equal to 0.
Sir,
What is the behavior of this circuit if I give external S0 or S1 and R0? Yes, you can tell now.
Sir, my question is it possible to analyze using S equal to 0? If we know that S equal to 1, we will get the output S, so that we came to know Q1, Q bar values. Both are S equal to 0, R equal to 0.
That is what I said. If you put S is equal to 0, R is equal to 0 in your NOR latch, what happening? Just it preserve the previous data. If you start analyzing from S0, R0, it just holds what it was earlier. Whatever the value of Q1, Q bar, it holds that. That is what mechanism I was explaining here. You can see. See, exclusively if I put S1 and R0, I am getting Q is equal to 1 and Q bar is equal to 0. Say for example, you are saying that if I'm putting S is equal to 0, R is equal to 0 to this circuit, correct? This is what your question.
Yes, sir.
What happens in this case is nothing but it just holds what it was earlier. If Q is equal to 0, it holds Q is equal to 0. Q bar is equal to 1, it holds Q bar is equal to 1. If this is 1, it holds 1. If this is 0, it holds 0. This is acting as memory here.
You are saying 0, 0 case after giving 1, 0 analysis, no, sir?
That is what, man. See, now which one? Kannada, Telugu, which one you are comfortable with?
Telugu, sir.
ఇప్పుడు చూడి S1 R0. Okay, other you can ignore me for just 2 or 3 minutes. I'll be speaking in English. Here, see, I'm giving S1 and R0. S is equal to 1 పెట్టి R0 పెట్టి Q1 అయింది, Q1 0 అయింది. దాని తర్వాత S0 R0 పెడితే నేను ಯಾವುದೇ స్టేట్ తర్వాత S0 R0 పెడితే ఏమైతుందంటే ప్రీవియస్ స్టేట్ ని ఫాలో అవుతుంది అని చెప్తా ఉన్నాను. అందుకే ఇక్కడ కూడా అంతే, S0 R1 పెడితే Q0 Q bar 1 అయింది, S0 R0 పెడితే ఇట్ జస్ట్ ప్రీవియస్ డేటా ఏముందో అదే రిటర్న్ అయింది అని చెప్తుంది కదా. ఈ S0 R0 అనేది ఇప్పుడు చూడి, ఈ స్టేట్ అయిన తర్వాతను పెడితే కదా, ఈ స్టేట్ అయిన తర్వాతను పెడితే, ఈ స్టేట్ అయిన తర్వాతను పెడితే